In this video, we're going to look at the Michael edition. Let's jump right in. We have seen previously that a nucleophile can backside attack a carbonyl. Electrons could go up onto the carbonyl, and the nucleophile can attack like that. We call this 1,2 addition because the nucleophile attacked carbon 2 and the negative ends up on the oxygen. But when I have a carbonyl that is conjugated, that means it's double, single, double, conjugated carbonyl, sometimes the nucleophile can attack this carbon. And the reason it can is because those electrons can push up to here, and they can push all the way up to the oxygen still, even though I attack this bottom carbon. So the nucleophile attacks there. Now I have a double bond here, and I still have an O minus. If this is carbon 1 or spot 1, the nucleophile attacked carbon 4, so some people call this 1,4 addition. Or others, because I attack a conjugated carbonyl, call it conjugate addition. Now, whether it attacks the carbonyl or the conjugated carbon, 1,2 or 1,4 addition, depends on what type of nucleophile is used. So, we're going to look at this particular example, and whenever the nucleophile is an enolate, we get the 1,4 addition, or what we call Michael addition. So let's look at an enolate attacking the conjugated part of this ketone. In the Michael addition, often we use a base to deprotonate this spot right between two carbonyl carbons, because those are the most acidic hydrogens, because I can have a negative charge, I can push up to one oxygen or the other oxygen through resonance forms. So once I have that negative enolate, if I have a conjugated carbonyl, the enolate attacks the fourth carbon for 1,4 addition. The electrons go all the way up to the oxygen to make. So on this fourth carbon is my enolate. Then what happens is I often run this reaction in alcohol. These electrons come back down and they grab that proton to turn that double bond into a single bond. So I reform my carbonyl. I have a single bond, and my enolate. That is the Michael product. That's the final product of my Michael addition. So let me show you how to jump right to the product without going through the entire mechanism. If I have a base, an enolate is formed, and you have a conjugated carbonyl, if you're doing a Michael addition, let me redraw these in a better format. Once you figure out which carbon is attacking the conjugated carbonyl, draw those next to each other. Then what you do is you connect here and turn this into a single bond. Everything else is the same. This spot becomes a single bond and you attach it to the enolate. That's the final product for the Michael addition. So in a Michael reaction, we have Michael donors and Michael acceptors. The donors are the things with a negative charge. They'll donate their electrons. And the spot right between two carbonyls is a great spot. But it doesn't have to be a carbonyl. It can be other things like carbonyls that can accept those electrons. So for example, a cyano group or a nitrile works. You can push those electrons all the way to the nitrogen. Or NO2 groups also work really well. Let me redraw the NO2 and you'll see why. That negative charge can go all the way up to that oxygen. So those are great spots to make a negative charge between two carbonyls next to cyano or next to nitro groups. Michael acceptors are conjugated carbonyl compounds. So any conjugated carbonyl. But again, it doesn't have to be a carbonyl. It could be a cyano group because they can accept the electrons. It could be a nitro group because it can accept the electrons. So carbonyl, cyano, nitros all work for Michael donors and Michael acceptors. Hey, I hope that's helpful. Subscribe to the channel so I can continue to help you with organic chemistry.